Space, the final frontier. A vast realm filled with possibilities and mysteries that have fascinated humanity for thousands of years. From the immense cosmic voids scattered across the universe to the very beginning of time itself, the cosmos invites us into a story far larger than our own world. Tonight, we begin a journey across that immense stage, exploring the deepest enigmas of the universe and reflecting on what its future might hold. Together, we will travel back to the earliest moments after the birth of the universe. We will watch how the cosmos evolved, how matter gathered into galaxies and stars, and then we will look forward into the unimaginably distant future. Along the way, we will search for the boundaries of the cosmos and ask a question that has puzzled scientists and philosophers alike. Is there truly an edge to everything we know? Or is the universe something far stranger than an endless space with walls around it? Hidden within the vastness of the universe lies a mystery that continues to challenge our understanding. It is a mystery that ignites imagination and pushes the limits of human thought. A question both simple and profound. What lies beyond the universe? As we look deeper into space, we eventually encounter an uncomfortable realization. Our view of the cosmos is limited. Everything we observe is confined within what scientists call the observable universe. Beyond that boundary lies a region we cannot see. Not because it does not exist, but because light from those regions has never had enough time to reach us. What lies beyond remains hidden behind a kind of cosmic curtain, concealing the deeper secrets of existence. The very idea of something beyond the universe quickly becomes a philosophical puzzle. How can we even imagine a region that exists outside everything we are able to observe? How do we think about a place that may lie forever beyond the reach of our senses and instruments? These questions stretch the limits of human reasoning. And yet they are precisely the questions that drive science forward. Curiosity pushes us to search for answers, even when the answers may lie far beyond our current understanding. Everything we can see around us, from the inside of a room to the most distant galaxies detected by powerful telescopes, belongs to what we call the observable universe. If light from an object can travel through space and eventually reach our eyes or our instruments, then that object is part of this observable region. In other words, the observable universe contains everything whose light has had time to arrive here since the beginning of cosmic history. According to current scientific measurements, the radius of the observable universe is about 46.5 billion light-years. Yet the age of the universe itself is estimated to be only about 13.8 billion years. At first glance, this seems impossible. If the universe is 13.8 billion years old, how can we see objects that are more than 46 billion light-years away? The answer lies in the expansion of the universe. Space itself is stretching. As light travels toward us across billions of years, the fabric of space through which it moves continues to expand. The galaxies that emitted that light have been carried farther and farther away during the time the light was traveling. By the time their ancient light finally reaches us, those galaxies are no longer where they once were. They now lie at far greater distances. Because of this expansion, the most distant regions we can observe today appear roughly 46.5 billion light-years away. This distance marks the limit of our observable universe. Beyond that boundary, there may be countless more galaxies and cosmic structures, perhaps extending infinitely. But modern cosmology cannot yet tell us what lies beyond the region whose light we are able to detect. These limits are known as cosmic horizons. They are not physical walls surrounding the universe, but boundaries created by the behavior of light itself. The speed of light is finite, and because the universe has existed for a limited amount of time, there are regions whose light simply has not had enough time to reach Earth. That is why the night sky is not completely filled with stars. The darkness between them is not necessarily empty. Much of it may simply lie beyond the reach of the light that could reveal it. For example, light itself sets a fundamental limit on what we can observe. There is a maximum distance from which light has had enough time to reach observers on Earth. You can imagine this as if there were a vast invisible sphere surrounding us. Beyond that sphere, there may be billions of other stars and galaxies. But their light has simply not arrived yet. This boundary is described through several important concepts in cosmology, including what scientists call the particle horizon and the event horizon. Although these terms sound similar, they describe different limits of the observable universe. The particle horizon refers to the greatest distance from which light emitted in the past has been able to reach us by the present moment. In other words, it defines how far we can currently see into the universe. The event horizon, on the other hand, describes a different boundary. It represents the distance beyond which events happening today will never be able to send signals that reach us in the future. Beyond these two limits lies another important boundary known as the Hubble horizon. If cosmic objects lie beyond this distance, the expansion of space carries them away from us so rapidly that their light can never catch up. Even across billions of years, they continue moving away at an effective speed comparable to the speed of light. Because of this, the universe can appear limited from our perspective. In reality, it is not the universe itself that is limited, but the light that allows us to observe it. Light does not travel infinitely fast. Every signal we receive from the cosmos requires time to cross the vast distances of space. Consider our own sun. It is located about 94 million miles from Earth. And even light moving at its incredible speed takes roughly 8 minutes to reach us. When we look at the sun, we are seeing it as it existed 8 minutes ago. Now consider the nearest star beyond our solar system, Proxima Centauri. It lies about 4.2 light-years away from Earth. Light leaving that star requires 4.2 years to reach us. When astronomers observe Proxima Centauri through a telescope, they are seeing the star not as it exists now, but as it appeared more than 4 years in the past. This means that when we look out into the night sky, we are also looking backward through time. Every distant object reveals a piece of cosmic history. The farther away the object is, the farther back in time we are seeing it. Take the galaxy known as HD1 as an example. It lies approximately 13.4 billion light-years away. The light we detect from this galaxy began its journey when the universe itself was extremely young. By observing such distant galaxies, astronomers are effectively studying the early chapters of cosmic history and learning how the first galaxies formed after the birth of the universe. Because of this, the detection of light from distant objects is one of the most powerful tools in cosmology. By studying ancient light, scientists have been able to reconstruct the story of how the universe evolved. One of the greatest breakthroughs that came from this effort was the development of the Big Bang theory. If the universe truly began in an extremely hot and dense state, that event should have left behind observable evidence. And in the 20th century, scientists discovered exactly such a signal. Two radio astronomers, Arno Penzias and Robert Wilson, were studying radio noise using a sensitive antenna when they detected a faint microwave signal coming from every direction in the sky. The signal had exactly the same intensity everywhere. What they had discovered was the cosmic microwave background radiation, the faint afterglow of the first light that filled the universe. In the earliest moments after the Big Bang, the universe was so hot that atoms could not form. Electrons and protons could not combine because the intense energy constantly tore them apart. Photons, the particles of light, were scattered in every direction by these charged particles. Light could not travel freely through space. The universe at that time was more like a dense, glowing fog than the transparent cosmos we see today. But as the universe expanded, it began to cool. Roughly 380,000 years after the Big Bang, conditions finally became cool enough for electrons and protons to combine into stable atoms. When that happened, the fog suddenly cleared. Space became transparent. and light was finally able to travel freely across enormous distances. That ancient light still fills the universe today. Over billions of years of cosmic expansion, its wavelength has stretched, and its energy has decreased. What was once extremely hot, radiation has cooled to a temperature just slightly above absolute zero, about minus 454 degrees Fahrenheit. Today we detect this radiation not as visible light, but as faint microwave signals arriving from every direction in the sky. This radiation reaches us from regions about 13.8 billion light-years away, because the light began its journey shortly after the birth of the universe. This distance also helps scientists estimate the age of the cosmos itself. Yet, even this remarkable signal does not necessarily show us the true age of the universe. It may simply represent the limit of what we are able to observe. And despite its profound importance, the cosmic microwave background cannot be seen with the human eye. The radiation is far too faint and exists at wavelengths outside the visible spectrum. Only highly sensitive instruments can detect it, allowing scientists to glimpse the earliest light that ever traveled across the universe. This effect happens because the universe itself is expanding. As space stretches, the light traveling through it stretches as well. Its wavelength grows longer, and its energy slowly decreases over billions of years. This process shifts the ancient light of the universe into the microwave region of the electromagnetic spectrum. What was once an intense glow is now an extremely faint signal, almost invisible, detectable only with highly sensitive instruments. Yet, even in this weakened form, that ancient radiation gives us something extraordinary. It allows scientists to peer through a narrow crack into the earliest moments of the universe. In a sense, it is a fossil record of the cosmos, a snapshot of the universe when it was only a few 100,000 years old. By carefully mapping this radiation across the entire sky, scientists have been able to reconstruct a remarkably detailed picture of the early universe. The cosmic microwave background forms a subtle pattern of temperature fluctuations. When these maps are visualized, they appear as a mottled surface. Blue regions represent areas slightly cooler than average, while orange regions represent areas slightly warmer. At first glance, the pattern seems random, but it contains profound information. These tiny variations in temperature reflect small differences in density that existed in the young universe. Those density variations acted as the seeds of structure formation over billions of years. Gravity amplified them, eventually producing the stars, galaxies, and galaxy clusters we observe today. The largest temperature patterns, spanning roughly 1 degree across the sky, provided crucial evidence that the geometry of the universe is essentially flat on cosmic scales. This was a remarkable confirmation of predictions made by cosmological theory decades earlier. Smaller fluctuations in the radiation carry even more information. By analyzing them, scientists have been able to determine the composition of the universe with astonishing precision. These measurements reveal that the matter we are familiar with, the atoms that form stars, planets, and people, represents only a small fraction of the cosmos. The majority of the universe consists of two mysterious components. About 26% is dark matter, an invisible form of matter that interacts gravitationally but does not emit light. Even more surprising, roughly 68% of the universe is dark energy, a still poorly understood phenomenon that appears to drive the accelerated expansion of space itself. These measurements were refined in the early 2000s by detailed observations of the cosmic microwave background. By studying the patterns in this radiation, researchers were able to calculate not only the composition of the universe, but also its age and its rate of expansion. The microwave background therefore acts like a cosmic archive. Encoded in its faint patterns is a vast amount of information about the early universe and about the processes that shape the cosmos over billions of years. It allows scientists to connect the distant past with the present structure of the universe, and even to make predictions about its future evolution. Yet despite all the knowledge it provides, there remains a fundamental limitation. Both the cosmic microwave background and the horizons of space restrict what we can observe from Earth. They mark the boundary of the observable universe, the region from which light has had time to reach us. This brings us to an important question. What exactly are these cosmic horizons? And is it possible, even in principle, to see beyond them? The particle horizon, as we mentioned earlier, is an imaginary boundary surrounding the observable universe. It represents the maximum distance from which light emitted in the past could have traveled to us since the beginning of cosmic time. If an object lies beyond that boundary, its light simply has not had enough time to reach Earth. However, this horizon is not fixed. As time passes, light from more distant regions continues its long journey through space. Gradually, over immense stretches of cosmic time, new objects enter the observable universe. With more powerful telescopes and instruments, we are able to detect signals from regions that were once hidden from view. Even so, there will always remain regions beyond our reach. Some parts of the universe will forever lie outside our observable horizon, permanently inaccessible to observation. But nature occasionally offers subtle ways to glimpse information that would otherwise remain hidden. We may never see a star 100 billion light-years away directly. Yet certain properties of the universe allow indirect clues about regions far beyond our visual limits. One of the most intriguing possibilities involves one of the most elusive particles known in physics. Meet the neutrino. A neutrino is an incredibly small and nearly massless fundamental particle. Trillions of them pass through your body every second without leaving a trace. They rarely interact with matter, which makes them extraordinarily difficult to detect. Yet this very property also makes them unique messengers from the most distant and energetic regions of the universe. And in the next part of our journey, these ghost-like particles may offer a surprising hint about what lies beyond the limits of the light we can see. The neutrino has almost no interaction with matter. That means it can travel enormous distances through space almost completely unhindered, moving at speeds extremely close to the speed of light. Because neutrinos are produced by many powerful cosmic events, such as nuclear reactions inside stars, supernova explosions, and the violent environments around black holes, they can carry information about these processes across the universe, even from distances of billions of light-years away. In addition, neutrinos can change type during their journey through a process known as neutrino oscillation, effectively transforming between different flavors while traveling through space. It is precisely because of the extraordinary elusiveness of neutrinos that scientists have worked for decades to detect them. However, new generations of ultra-sensitive detectors buried deep underground or beneath Antarctic ice are beginning to capture these ghost-like particles with increasing accuracy. And so, in the future, thanks to these tiny particles, we may learn more about regions of the universe that light itself cannot easily reveal, possibly giving us indirect clues about what lies beyond the cosmic horizon. In addition to neutrinos, gravitational waves also provide a new way to explore the universe beyond what traditional telescopes can see. These ripples in space-time are produced when extremely massive objects accelerate, especially during events like the merger of black holes, neutron stars, or the rapid orbital motion of dense stellar remnants. As a result of such immense cosmic events, these waves spread outward in all directions at the speed of light, gently stretching and compressing space-time itself as they pass. By the time they reach Earth, the distortions they create are incredibly small, far smaller than the width of a single atomic nucleus, which makes them extraordinarily difficult to detect. Even so, These faint space-time ripples allow scientists to reconstruct events that happened billions of light years away. For example, in 2015, scientists working with the LIGO observatories detected the first gravitational waves produced by the merger of two black holes about 1.3 billion light-years from Earth. Confirming a prediction Einstein made a century earlier, gravitational waves, like neutrinos, therefore act as new messengers from the distant universe, allowing us to observe phenomena that may be invisible through ordinary light. As our detection technologies improve, they may help reveal events occurring in regions that lie near or even beyond the limits of the observable universe. But no matter how rapidly our ability to study the cosmos advances, we are still limited by one fundamental factor: the expansion of the universe itself. Since the Big Bang, space has been expanding. At first, this expansion slowed down under the influence of gravity. But billions of years later, something unexpected happened. The expansion began to accelerate, driven not by dark matter as once thought, but by a mysterious component known as dark energy that permeates the universe. Because of this expansion, distant galaxies are constantly moving away from us. The farther away a galaxy is, the faster it appears to recede. This relationship is described by Hubble's law, which shows that cosmic expansion increases with distance. The particle horizon therefore grows as the universe evolves. Over time, light from more distant regions can finally reach us, meaning that the observable universe slowly expands. As this horizon grows, objects that were once beyond our observational reach may gradually appear on our cosmic maps. However, this does not mean we will eventually see everything. In fact, the opposite may occur on extremely long timescales. Because the expansion of the universe is accelerating, many galaxies are moving away from us so quickly that their light will never reach Earth. These galaxies will eventually slip beyond another boundary known as the cosmic event horizon. The event horizon sets a fundamental limit for the universe. Beyond this distance, any signal emitted today will never be able to reach us, no matter how long we wait. Light, neutrinos, and even gravitational waves emitted from those regions will forever remain beyond our reach. And so the observable universe, vast as it is, may represent only a small island of visibility within a far larger cosmic ocean. Currently, the radius of the cosmic event horizon is roughly 16 billion light-years. So even if a galaxy lies within our observable universe, but beyond the event horizon, we will never be able to interact with it. Any signal emitted today, for example, a radio transmission from Earth, will stretch as the universe expands. Over time, the wavelength becomes longer and longer until the signal fades into frequencies too weak and too stretched for any civilization to detect. Meanwhile, the galaxy receiving that signal would continue moving farther away from us as space expands. Because of this, it may be impossible for us to make our presence known to extraterrestrial civilizations located extremely far away. In fact, in the distant future, even galaxies that are currently visible and potentially reachable may eventually drift beyond our ability to communicate with them. This gradual separation is driven by the accelerating expansion of the universe. The size of the event horizon has changed over cosmic history. In the very early universe, it was effectively much larger relative to observable distances. But today, it stabilizes at roughly 16 billion light-years. In the far future, this boundary will slowly become more restrictive for communication. If that happens, humanity could eventually find itself inside an isolated cosmic bubble, surrounded by regions of space that can never exchange signals with us. And forming another layer of this cosmic boundary is a concept known as the Hubble horizon. This limit corresponds to the distance at which the recession velocity of galaxies caused by cosmic expansion equals the speed of light. Today, this distance is roughly 14 to 15 billion light-years. Beyond this point, the expansion of space carries galaxies away from us so rapidly that light emitted today can no longer make progress toward Earth. For a photon, it becomes something like an endless race against the expansion of space itself. The farther away the source of light is, the faster space between us expands. In regions beyond the Hubble horizon, the expansion effectively wins the race. However, the Hubble horizon itself is not fixed. Because cosmic expansion changes over time, the horizon can slowly evolve, allowing some distant light that was once receding to eventually cross back into the observable universe. This is why astronomers are still able to detect extremely distant galaxies whose light began traveling toward us billions of years ago. Yet expansion also has another consequence. Over unimaginably long timescales, the observable universe will gradually shrink from our perspective. In the very distant future, tens or hundreds of billions of years from now, the accelerating expansion driven by dark energy will push most galaxies beyond our cosmic horizon. At that stage, observers inside our galaxy will see only the local group of galaxies, including the Milky Way and Andromeda. All other galaxies will have faded beyond detectability. Their light will be stretched so severely by cosmic expansion that it will never reach us again. In effect, the observable universe will appear to collapse around us. Not because the universe itself is shrinking, but because the expansion of space isolates regions of the cosmos from each other. Some theoretical models suggest that over extremely long cosmic timescales, the event horizon and the Hubble horizon will approach similar scales, creating a stable boundary that limits the region of space from which signals can ever reach us. Beyond that boundary, events will occur forever unseen. This means that although the universe may be far larger than the observable region we inhabit, our ability to study it will always be limited by these cosmic horizons. They form invisible spherical boundaries surrounding us, preventing distant light from ever reaching Earth. In the far future, these limits could become even more restrictive. Humanity, or whatever civilizations may exist then, might find themselves cosmically isolated, surrounded by darkness where once there were countless galaxies. And yet, despite these limits, our curiosity continues to push outward. New technologies are already opening windows into parts of the universe that traditional telescopes cannot easily reach. Neutrino observatories and gravitational wave detectors allow us to observe violent cosmic events across enormous distances, even when no visible light is produced. As detection technology improves, these new messengers may reveal more information about the deep universe, offering indirect glimpses of regions close to, or perhaps even beyond the limits of our current observable horizon. And perhaps one day, future civilizations may extend their observatories beyond Earth, placing detectors across the solar system or on distant worlds, establishing new vantage points from which to observe the cosmos. We may never escape the fundamental limits imposed by the structure of space-time itself, but with patience, ingenuity, and curiosity, we can learn to explore right up to the edge of those limits. And sometimes, that is where the most interesting discoveries begin. It may take many generations before humanity can truly reach the limits of our observable horizon, let alone move beyond it. But if that day ever comes, we will discover that there is not just one horizon waiting for us. Instead, there will be countless others, each revealing a new boundary, a new layer of the cosmos waiting to be understood. For as long as our species has existed, we have looked up into the night sky and wondered about the vastness of the universe. We have counted the stars, traced the constellations, and imagined what might lie beyond our tiny corner of the cosmos. But have we ever truly dared to think about the end, not the end of a single human life, or even the end of civilizations, but the end of time itself? What will the final days of the universe look like? What will exist in those last moments? Will the cosmos end in a sudden, violent collapse, or fade slowly into silence and darkness? Throughout history, humanity has been driven by curiosity. We have crossed oceans, climbed mountains, and launched machines beyond our planet in search of answers. Today, we embark on a journey even deeper than space. A journey across time itself, like grains of sand slipping through an hourglass. Every passing moment brings the universe closer to whatever final state awaits it. The question is not whether the universe will change, but how. How will it end, and what does that mean for beings like us? Fragile creatures living for only a brief moment within cosmic history. To explore these questions, we must travel far beyond ordinary imagination. Not across distance, but across billions, trillions, and perhaps even quadrillions of years into the future. This is not a journey through space. It is a journey through time toward the ultimate fate of the universe. And that journey begins here, in our own era. We are living in what many scientists call the Anthropocene, the age of human influence. It is a period defined by the extraordinary impact our species has had on the small blue world we call home. In only a few centuries, humanity has altered landscapes, oceans, and even the atmosphere itself. On the scale of cosmic history, this transformation happened in the blink of an eye. Before the Anthropocene came the Holocene, a period that began roughly 11,700 years ago. After the end of the last ice age, during this long and remarkably stable era, human civilization was born. The relatively gentle climate of the Holocene allowed agriculture to develop. Settlements grew into cities. Writing, innovations, science, and culture emerged. Civilizations flourished across the planet. In many ways, the Holocene was the environmental foundation that allowed humanity to become what it is today. But as our technological power grew, so did our impact on the Earth. Our demand for energy, land, and resources reshaped ecosystems around the globe. Forests were cleared, oceans were overfished, and the delicate balance of Earth's climate system began to shift. Today we can see the consequences of those changes unfolding. Climate patterns are shifting. Extreme weather events are becoming more frequent. Entire ecosystems are under pressure. Biodiversity is declining at a rate rarely seen in geological history. The equilibrium that supported human civilization for thousands of years now appears increasingly fragile. The world that nurtured our species may be entering a new and uncertain chapter. And yet, even these dramatic changes on Earth are only a tiny moment in the far larger story of the universe. Because while humanity debates the future of our planet, the universe itself is moving steadily forward in time, toward a future far stranger and far more distant than anything we experience today. Our actions have left an indelible mark on the conditions of the Earth and ushered in a new geological epoch, the Anthropocene. This is a chapter of Earth's history written by human hands. As we stand on the threshold of this new era, one question arises. What legacy will we leave to succeeding eras? Our journey brings us closer to the year 2500, revealing the dynamic changes the Earth may face. Earth's magnetic field, our protective shield against solar winds, is undergoing a gradual shift. The North and South poles are slowly moving and may eventually reverse. An event last observed about 780,000 years ago. This remarkable process could disrupt navigation systems and satellite technology, forcing humanity to adapt in ways never before experienced. Let us be transported to the year 4385. We witness the return of an old visitor, Comet Hale-Bopp. It becomes a breathtaking sight in the night sky. A bright trail of light stretching across the darkness and reminding us of our place in the universe. Jumping forward to the year 5000. We are confronted with the long-term consequences of past climate changes. Sea levels may have risen significantly, and many coastal regions that were once thriving centers of human life now lie beneath the ocean. Silent reminders of earlier centuries. By the year 6000, humanity may face another cosmic threat. A large asteroid passes dangerously close to Earth. Whether it collides or narrowly misses will depend on the ability of future civilizations to detect and redirect such objects, reminding us that planetary defense may one day become essential for survival. In the year 8000, we witness an extraordinary celestial event. A distant star reaches the end of its life and explodes in a brilliant supernova. For a brief moment, its glow rivals the brightness of entire galaxies. A powerful reminder that the universe is constantly changing. The Earth and the cosmos are always in motion. And this perpetual movement reminds us of the impermanence of our journey. As we gaze into the star-filled canvas of the universe, we reflect on the challenges that lie ahead as we travel toward the far future and the distant end of time. The cosmic clock moves forward 1 billion years. Our sun, the source of all life on Earth, begins to change dramatically. Its luminosity increases by about 10%. Slowly warming the planet. As temperatures continue to rise, photosynthesis begins to fail around 1.1 billion years from now. The green surface that once covered Earth gradually fades, replaced by increasingly barren landscapes. The atmosphere becomes thinner, and the oxygen that complex life depends on begins to disappear. The relentless heat continues to intensify. By about 1.3 billion years in the future, Earth's oceans begin to evaporate. What was once a blue world filled with water slowly transforms into a dry and hostile planet. The vast seas that shape the history of life become distant memories written only in the rocks. Our journey now approaches the final chapter of Earth's story. Around 7.5 billion years from now, the Sun expands into a red giant. As it swells outward, it engulfs the inner planets of the solar system. Eventually, it consumes Earth itself, marking the end of our home world. The planet that nurtured life for billions of years returns to the cosmic material from which it once formed. We move forward to 10 billion years in the future. After shedding its outer layers, the Sun settles into its final state as a white dwarf. It becomes a small, dense, slowly cooling remnant of its former self. The brilliant engine of nuclear fusion that once powered the solar system fades into a dim stellar ember, quietly drifting through space as the universe continues its long evolution. By 100 trillion years, a deep silence begins to settle across the cosmos. The stars that once filled the night sky gradually burn out one by one, and the universe slowly enters an era where light itself becomes increasingly rare. They leave behind a chilling darkness. A universe in twilight. By 1 quadrillion years, long after the last ordinary stars have vanished, the temperature of the universe continues to fall. Having begun in the intense heat of the Big Bang, the cosmos slowly sinks into a deep cosmic winter, the universe gradually slipping into darkness. The era of starlight is over. The universe has become a cosmic graveyard. What remain are the fading remnants of stars that once illuminated the cosmos. They glow with a faint and ghostly light, a distant echo of the universe's brilliant past. By 10 quadrillion years, these white dwarfs have become the dominant stellar objects in the universe. This period is often described as the degenerate era. It is a ghostly universe filled with the silent remains of galaxies and stars that once shone brightly. The age of extinction becomes a powerful reminder of the endless cycle of birth and death that shaped the cosmos for trillions of years. Yet, even in this fading universe, change never truly stops. Gravity, the great sculptor of cosmic structure, continues its quiet work. Gravity never rests. Over immense spans of time, it slowly destabilizes planetary systems and star remnants, sometimes tearing planets away from their orbits and sending them drifting through interstellar space. Occasionally, these interactions may cause two stellar remnants to collide. In extremely rare cases, such collisions could briefly reignite nuclear reactions, producing a short burst of light similar to a supernova, a final echo of the universe that once blazed with stars. Meanwhile, white dwarfs slowly continue their long descent toward darkness. Over trillions of years, they cool and fade. Their faint glow weakens until eventually it disappears completely. At that stage, they become what astronomers call black dwarfs, the final evolutionary state of a star that once shone, invisible and cold. These objects mark the universe's gradual descent into darkness. The era of black dwarfs begins. The universe, once a spectacle of light and color, is now only a shadow of its former self. The journey toward the end of time continues in silence, coldness, and darkness. As the universe ages, cosmic expansion continues relentlessly. Space itself stretches, causing galaxies and remaining objects to drift farther and farther apart. Regions of the universe become increasingly isolated from one another. What was once a structured cosmic web slowly transforms into something resembling countless distant islands scattered across an endless ocean of emptiness. Within this immense void, an even deeper transformation may occur. According to some theories in particle physics, protons, the fundamental building blocks of atoms, may not be perfectly stable. Over unimaginable periods of time, they may slowly decay. If this process occurs, every atom in the universe would eventually break apart. Protons could decay into lighter particles such as neutrinos, photons, and other elementary particles. If proton decay truly happens, matter as we know it would gradually disappear. The universe would slowly erase the last remaining traces of its physical structure. Planets, stars, and even the remnants of galaxies would dissolve into a thin sea of subatomic particles. Eventually, only radiation and black holes would remain. At this stage of the cosmic timeline, the familiar forms of matter and astrophysical processes come to an end. The universe enters an entirely new era of cosmic history, a time when only the most extreme objects and the most subtle physical processes continue to shape the fate of the cosmos. We now enter what astronomers often describe as the era of black holes. Even the seemingly eternal black dwarfs have largely disappeared, either drifting through empty space or gradually interacting with other remnants over unimaginable stretches of time. The last visible traces of stars have faded away, leaving only the faint debris of what were once luminous galaxies. Black holes have become the dominant celestial objects scattered throughout the universe. In this era dominated by black holes, the remnants of once thriving galaxies, supermassive black holes, play a particularly important role. Born from the collapse of massive stars and the gradual merging of smaller black holes over billions of years. These cosmic giants have grown to extraordinary sizes. They absorb surrounding matter and energy on scales far beyond anything that once existed in the earlier universe. When black holes merge, they release enormous bursts of gravitational waves, ripples that travel through the very fabric of space-time. We can imagine these waves as the final echoes of the universe, the slow ringing of a cosmic bell reverberating through the vast emptiness of space. These signals may represent the last dramatic events of a universe that once shone brightly with galaxies and stars. Yet even objects as powerful as black holes are not truly eternal. The famous physicist Stephen Hawking proposed in the late 1970s a remarkable idea now known as Hawking radiation. According to this theory, black holes slowly lose energy and therefore mass over extremely long periods of time. This process arises from quantum effects near the event horizon. At the smallest scales of physics, pairs of particles and antiparticles can briefly appear from the vacuum of space. Normally, they would annihilate each other almost instantly. However, near a black hole's event horizon, it is possible for one particle to fall into the black hole while the other escapes into space. When this happens, the escaping particle carries away energy. Over enormous spans of time, this causes the black hole to slowly lose mass. As a result, the black hole gradually shrinks. Its once overwhelming gravitational pull slowly weakens as the evaporation process continues. Eventually, after timescales far longer than the current age of the universe, even the largest black holes will evaporate completely. The disappearance of these final cosmic giants marks the end of the last major structures in the universe, leaving behind an immense and nearly empty cosmic void. Since the Big Bang, the universe has been expanding, driven in part by a mysterious phenomenon known as dark energy. This hypothetical form of energy appears to permeate all of space and act in opposition to gravity, causing the expansion of the universe to accelerate over time. At the same time, dark matter, which makes up about 85% of the total matter in the universe, provides gravitational attraction. It helps shape galaxies and cosmic structures, acting as a counterbalance to the expansive influence of dark energy. Although dark energy appears to dominate the large-scale behavior of the universe today, scientists continue to explore the possibility that the balance between these cosmic forces could change over extremely long periods of time. Some theoretical ideas suggest that the behavior of dark energy itself may evolve, potentially altering the future expansion of the universe in ways we do not yet fully understand. If the gravitational influence of dark matter were ever to exceed the force of dark energy, the expansion of the universe could begin to slow down and possibly even reverse. This scenario is sometimes compared to the effect of a stretched elastic band, where expansion continues for a long time before a sudden contraction begins. Such a hypothetical process is often referred to as the Big Crunch. During this phase of contraction, the universe would gradually collapse inward. The density of matter and energy would increase dramatically as galaxies, stars, and all cosmic structures move closer together. Eventually, the universe could reach an extreme state where temperatures and densities rise to unimaginable levels. At the final stage of this collapse, everything that exists could be compressed into an extraordinarily dense state, approaching a singularity. In such conditions, the familiar laws of space and time would break down. Physics, as we currently understand it, would no longer be able to describe what happens next. Some theoretical models suggest that in this extreme state, a new expansion event could occur, potentially giving rise to another Big Bang and the birth of a new universe. In that sense, cosmic history might unfold as a sequence of cycles, where one universe ends and another begins. Reflecting on this journey gives us a profound sense of our place in the cosmos. Our entire existence occupies only a brief moment within the immense timeline of the universe. The journey to the end of time eventually leads us back to the beginning. And perhaps this is where the greatest insight lies. In a universe filled with endless possibilities, the end may simply become the starting point for something new. Many of us have wondered what the distant future might look like. What will happen in 100 years, 1,000 years, or even 1,000,000 years from now? To explore that question, we can look at the long-term evolution of the stars that fill our night sky. By following their life cycles, scientists can imagine how the universe may change over immense periods of time. Today, we attempt to look beyond the veil of the future, tracing the evolution of the cosmos from the stars we see every night, all the way toward the farthest imaginable future. We will attempt to follow the story of time itself and ask what the universe might look like in 100 million years. In a sense, this journey allows us to move both forward and backward through cosmic history. In only a few moments of imagination, we can travel from the earliest stages of the universe all the way toward its distant future. Of course, nothing in the universe lasts forever, over extremely long timescales. Even the stars themselves will change and eventually disappear. In 100 million years, many of the most massive stars we see today will already have ended their lives, leaving behind expanding clouds of gas and dust known as nebulae. Stars are born from enormous molecular clouds composed primarily of hydrogen gas and microscopic grains of dust. Under the influence of gravity, these clouds slowly collapse and form new stars over periods of tens of millions of years. Once formed, a star can shine steadily for millions or even billions of years depending on its mass. During most of a star's lifetime, it appears relatively stable. Yet deep within its core, nuclear reactions continuously convert hydrogen into helium. Over time, this gradual transformation alters the internal structure of the star. As hydrogen fuel becomes depleted, the core contracts, while the outer layers respond by changing temperature and brightness, beginning the next stage in the star's long evolution. The final stage of a star's life eventually begins, lasting far shorter than the long, stable period during which it shines. Stars with masses similar to our Sun, after roughly 9 to 10 billion years, expand into red giants. In this phase, their outer layers swell enormously while their cores continue to evolve. After some time, these stars shed their outer layers into space, creating glowing clouds of gas and dust. What remains behind is a dense stellar remnant known as a white dwarf, surrounded by a faint expanding nebula from which new generations of stars may one day form. However, even a period of 100 million years will bring noticeable changes to our own Sun. During that time, the Sun will slowly become brighter and hotter, increasing its luminosity by roughly 1%. This gradual change may seem small, but over long timescales, it can significantly affect the climate of Earth. Looking even further ahead, in roughly 1 to 2 billion years, the Sun will grow bright enough that conditions on Earth could become hostile to complex life. But what if such processes could one day be slowed or even controlled? Although 100 million years is an almost unimaginable span of time for humanity, it is still a brief moment on cosmic timescales. Over such vast periods, technological civilizations might advance to levels that today sound like science fiction. In a future that distant, humanity might develop the ability to influence stellar evolution itself, through concepts sometimes referred to as stellar engineering. Advanced civilizations could theoretically regulate the energy output of stars or alter the processes occurring inside them. During such an era, it is possible to imagine technologies capable of managing a star's fuel supply or carefully modifying its nuclear reactions, extending the lifetime of stars far beyond their natural limits. Then the Sun could survive longer and no longer pose a threat to life on our planet. The ability to manipulate stars could also create conditions suitable for life on planets that are not currently considered habitable. In particular, future civilizations might learn to extract hydrogen and helium directly from stellar environments, using them as powerful sources of energy. Human civilization could expand to an extraordinary scale. The resources available on planets alone might no longer be sufficient to support such a vast population. For this reason, advanced societies may turn toward the direct harvesting of stellar energy. One concept often discussed by physicists is the Dyson sphere, a theoretical structure designed to capture a large fraction of the energy emitted by a star. By collecting this energy close to the star itself, Such systems could provide enormous power supplies while preserving the resources and ecosystems of inhabited planets. On the other hand, manipulating stars could also carry risks. If stellar engineering were used to accelerate the aging of stars by extracting large amounts of fuel, the regions around those stars could become unstable and dangerous for nearby planets. In such scenarios, entire galaxies might experience accelerated stellar evolution as their stars age and fade more rapidly than they naturally would. Time affects not only stars but also galaxies. The galaxies we observe today formed early in the history of the universe and have continued evolving ever since. Over billions of years they move, interact, and sometimes merge with one another, before galaxies eventually fade. They pass through long stages of transformation. Smaller galaxies are gradually absorbed by larger ones through gravitational interactions. Because of this process, over very long timescales, the number of small isolated galaxies decreases, while larger galaxies grow in mass and complexity. Even within the next 100 million years, astronomers expect subtle changes in the distribution of galaxies. Some smaller galaxies may be pulled into larger systems, and the balance between spiral and elliptical galaxies could shift slightly as gravitational interactions reshape them. Future civilizations observing the sky may witness many examples of galaxy mergers, particularly involving smaller galaxies. These encounters can trigger new waves of star formation and reshape galactic structures. In some cases, they may also contribute to the growth of supermassive black holes at the centers of galaxies. Our own galaxy, the Milky Way, is also moving through space toward a future encounter. It is gradually approaching the Andromeda Galaxy, our nearest large galactic neighbor. Fortunately, there is no reason for concern in the near future. Even though the two galaxies are slowly drawing closer together, their collision is expected to occur in about 5 billion years. Over the next 100 million years, the Milky Way itself will travel roughly 978,000 light-years through space. On human timescales, this movement is almost impossible to imagine. Yet, on the scale of galaxies, it is a relatively small shift and will have little direct effect on our region of the galaxy. As galaxies continue moving through the cosmic web, they pass through regions with different densities of matter. These environments influence their shapes, their internal structures, and the rate at which new stars are formed. But even the most beautiful galaxies will not shine forever. Over time, their brightness gradually fades as their most massive stars complete their life cycles and explode as supernovas. These massive stars play a major role in determining the color and brightness of galaxies. As they disappear, galaxies slowly lose some of their brilliance. After each stellar explosion, much of the gas released remains trapped within the galaxy, allowing new stars to form and keeping the galaxy active for long periods of time. However, some of that gas escapes into intergalactic space, slowly reducing the raw material available for future star formation. Over immense spans of time, this gradual loss contributes to the fading of galaxies across the universe. Because of this, fewer massive stars are formed over time. As star formation slows, the overall mass and brightness of galaxies gradually decline over extremely long periods. Many galaxies may lose most of their visible structure, leaving behind only their central supermassive black holes as the dominant remaining objects. In fact, it is almost impossible to find anything truly static in our universe. Everything is in motion. Planets orbit stars. Stars move through galaxies, and galaxies themselves drift through the vast cosmic web. Even the universe as a whole is constantly changing. Since the moment of the Big Bang, the universe has never stopped expanding. In the earliest moments of cosmic history, during a period known as cosmic inflation, space expanded at an extraordinary rate. effectively faster than light due to the expansion of space-time itself. Later, as the universe cooled and matter formed from elementary particles such as protons, neutrons, and electrons, the expansion slowed. For billions of years, gravity partially resisted this expansion. However, about 5 billion years ago, the situation changed. The expansion of the universe began to accelerate again. Today, and far into the future, the universe will continue expanding. It is important to understand that this expansion does not mean that galaxies are simply flying through space like objects in an explosion. Instead, space itself is stretching. A useful analogy is a balloon with two dots drawn on its surface. As the balloon inflates, the dots move farther apart even though neither dot is actively moving across the surface. This expansion has little effect on systems bound together by gravity. Galaxies such as the Milky Way and Andromeda remain gravitationally connected. And even the solar system and our own planet remain stable despite the expansion of the universe around them. The total amount of ordinary matter and dark matter in the universe remains essentially constant. What changes is the distribution of that matter as space expands and the average density of matter decreases across ever larger volumes of space. Because of this expansion, we observe distant galaxies moving away from us. Looking ahead 100 million years, the galaxies of the local group will have shifted slightly in position relative to our current view of the sky. Their motion will not make them disappear, but their positions will slowly change over cosmic time. Meanwhile, extremely distant galaxy clusters such as CLJ 1001 plus 0220 may appear even fainter as the expansion of the universe stretches the light traveling toward us. The expansion of the universe is also accelerating. This acceleration is driven by a mysterious component of the cosmos known as dark energy. Measurements of distant galaxies show that the farther away a galaxy is, the faster it appears to recede from us. A relationship described by Hubble's law. Over extremely large distances, this recession becomes enormous. If cosmic expansion continues accelerating, the formation of new cosmic structures may gradually become more difficult. Regions of gas and dust could be pulled apart before gravity has time to gather them into new stars or galaxies. The main factor behind this possibility is dark energy, which appears to counteract the gravitational attraction of matter on the largest scales of the universe. Dark energy remains one of the greatest mysteries in modern cosmology. It may represent a property of empty space itself, influencing how the universe evolves over billions of years. If its effects continue to dominate cosmic expansion, there may come a time when galaxies no longer merge and large-scale cosmic structures stop growing. Over long periods, the gas and dust released by dying stars could become too dispersed to collapse into new stars. Star formation would slow dramatically. Eventually, after billions of years, the raw material needed to create new stars might become too thinly spread throughout space. In that distant future, no new stars, galaxies, or planetary systems would form. Instead, the universe would slowly approach a state known as heat death. This does not mean the universe turns into a blazing inferno. Rather, it describes a future in which the universe becomes extremely cold and diffuse. Energy would be spread so evenly across space that no useful energy gradients remain to power stars, galaxies, or life. The scenario describing the future fate of the universe is based on the second law of thermodynamics, which states that in a closed system entropy, or the level of disorder, tends to increase over time. This means that energy gradually spreads out and becomes less concentrated. Eventually, it becomes so evenly distributed that nothing new can easily form from it. You can imagine this process in a simple way. When you pour a hot cup of tea, heat slowly leaves the tea and spreads throughout the room. After some time, the temperature of the tea becomes the same as the temperature of the surrounding air. At that point, the tea no longer feels warm because the heat energy has dissipated. In a similar way, the energy in the universe slowly spreads out across space over immense stretches of time. As this process continues, galaxies move farther and farther apart, and stars gradually fade away. Without fresh supplies of gas and energy, the processes that create stars, planets, and other cosmic structures begin to slow down and eventually stop. The universe slowly becomes darker and emptier. Dark energy may influence this future in several possible ways. In the simplest scenario, the universe continues expanding forever while star formation slowly fades. Over extremely long timescales, the cosmos approaches a state where almost no new structures can form. However, some theoretical models suggest more dramatic possibilities. If the expansion of the universe were to accelerate far more strongly than current observations indicate, the future could be very different. In such a scenario, the universe might approach a state sometimes described as a complete cosmic dissolution. In this case, the expansion of space would become so powerful that even gravitationally bound systems would struggle to remain intact. Stars would not simply stop forming. Instead, existing structures could gradually be pulled apart as the expansion of space-time grows stronger. One extreme theoretical possibility is known as the Big Rip. According to this idea, if dark energy continues to strengthen over time, the acceleration of cosmic expansion could eventually overwhelm all other forces. At first, galaxies would drift apart so rapidly that they could no longer remain gravitationally bound. Later, even smaller structures could be affected. Planets might eventually drift away from their stars as gravitational bonds weaken. With even more time, the forces that hold stars together might no longer be able to resist the accelerating expansion. In the farthest stages of this scenario, even atoms themselves could be torn apart as space-time expands faster than the forces that hold matter together. Some theoretical discussions also explore whether the universe could one day return to conditions similar to those near the beginning of cosmic history. In such speculative models, extreme physical conditions might again appear at enormous densities or energies. However, any future singular state would likely be very different from the hot plasma that existed shortly after the Big Bang. And scientists still do not know exactly what physics would govern such an environment. It would be cold and dilute rather than hot and dense. In other words, no matter how dramatic the hypothetical end of the universe might appear, there remains a possibility that such an ending could also represent the beginning of a new cosmic cycle. Another potential danger to the universe may lie hidden within the very particles that make up everything around us. We know that all matter is composed of atoms. At the center of every atom is a nucleus containing two main types of particles: protons and neutrons, surrounded by electrons. For a long time, scientists believed that protons were completely stable particles. The proton is one of the most abundant particles in the universe and can exist both inside atomic nuclei and as an isolated particle. Its apparent stability is connected to several conservation laws in physics, including the conservation of energy, electric charge, and baryon number. According to the traditional standard model of particle physics, the proton does not decay. However, some modern theoretical frameworks suggest a different possibility. In particular, theories known as grand unified theories attempt to combine the three fundamental forces of electromagnetism, the weak interaction, and the strong interaction into a single unified force. Within certain versions of these theories, the proton may not be perfectly stable after all. Instead, it could slowly decay over extraordinarily long periods of time. If proton decay exists, it would occur extremely rarely. Current experimental limits suggest that the lifetime of a proton would be far longer than 10 to the power of 34 years, vastly exceeding the current age of the universe. Yet, in the distant future, even such incredibly rare processes could begin to reshape the cosmos. On its own, proton decay would not suddenly destroy the universe. However, if it occurred everywhere over unimaginable timescales, atoms would gradually break apart. As protons decayed, the nuclei of atoms would become unstable, and matter itself would slowly transform into lighter particles such as photons and neutrinos. Even so, the universe would not vanish instantly. Instead, the familiar structures of matter would slowly dissolve. Galaxies, stars, planets, and even solid objects would eventually disintegrate as their atomic structures collapsed. Future civilizations, if any still existed during such epochs, might witness the gradual disappearance of matter itself. Yet proton decay is not the only theoretical possibility for the ultimate destruction of the universe. Some physicists have proposed another scenario involving the fundamental structure of the vacuum itself. This idea is sometimes referred to as vacuum decay. To understand this possibility, we must consider the role of the Higgs boson, a particle discovered in 2012 that is associated with the Higgs field. The Higgs field is believed to fill all of space, and particles gain mass through their interaction with this field. In quantum physics, what we call a vacuum is not truly empty space. Instead, it contains fluctuating quantum fields that hold a certain amount of energy. The energy state of these fields determines whether the vacuum of the universe is stable. Physicists describe two possible conditions. A true vacuum represents the lowest possible energy state of the universe and would be completely stable. A false vacuum, however, is a higher energy state that appears stable but may eventually transition to a lower energy configuration. Some calculations suggest that our universe might exist in such a metastable vacuum state. If that were true, then in principle the universe could one day transition to a true vacuum state through a quantum event. This transition would form an expanding bubble of new vacuum energy that spreads outward at nearly the speed of light, fundamentally altering the laws of physics inside it. Although this scenario remains highly speculative, it illustrates how the ultimate fate of the universe may depend not only on cosmic expansion or gravity, but also on the deepest quantum properties of reality itself. If, sometime in the distant future, perhaps 100 million years from now, an event of enormous energy were to occur in the universe, such as an extremely rare, large-scale proton decay event, a small region of space could hypothetically transition into what physicists call a true vacuum state. If that were to happen, a tiny bubble of true vacuum would form, and once such a bubble appeared, it would expand outward at the speed of light, rewriting the fundamental structure of reality as it moved. Everything in its path, atoms, molecules, stars, even the fundamental particles themselves, would be transformed into a new configuration of physics. In such a scenario, life as we understand it could not survive. The universe would not explode in a dramatic instant, but the familiar laws that shape matter, chemistry, and structure would simply cease to exist inside the expanding bubble. Yet even this possibility remains deeply theoretical. The truth is that the universe will continue to evolve for unimaginable spans of time, gradually changing in ways that future civilizations may struggle to recognize. Like every system governed by time and entropy, the cosmos itself will slowly transform. One day, far beyond any human lifetime, the universe may begin to fade. We do not know exactly when this will happen, and no matter how far our science advances, there will always remain limits to how accurately we can predict the ultimate future of reality. But one thing seems certain: humanity, or whatever descendants follow us, will continue to make extraordinary discoveries. perhaps millions of years from now, future scientists will finally uncover the full history of the universe. And in doing so, understand far more about the origins of matter, galaxies, and even ourselves. Space has always been called the final frontier, a vast cosmic tapestry filled with stars, galaxies, and glowing nebulae, all woven together by gravity and the hidden structure of space-time. But what happens when that tapestry appears to tear? What happens when astronomers discover a region so vast and so empty that it seems to challenge the very architecture of the universe? Imagine a region of space so enormous and so devoid of matter that even traveling at the speed of light, the fastest speed allowed by physics, it would take more than 300 million years to cross from one side to the other. That is more than 20 times larger than our entire Milky Way galaxy. Inside this region, galaxies are extraordinarily rare. The average density of matter is so low that it pushes the limits of what our models of cosmic structure predict. This is not science fiction. It is a real and mysterious feature of the universe known as a cosmic void. Welcome to one of the strangest landscapes in all of cosmology, the Great Void, a vast abyss where the universe appears to thin out into near nothingness, raising deep questions about how the cosmos formed and why its structure looks the way it does. To understand how astronomers discovered these immense empty regions, we must travel back in time to the earliest days of modern astronomy. In the late 18th century, a new era of observation began with the development of increasingly powerful telescopes. Astronomers started mapping the night sky with greater precision than ever before, cataloging stars and attempting to understand the structure of our galaxy. At the time, the Milky Way itself seemed unimaginably vast. Few could even imagine that it might be just one galaxy among billions. It was not until the 20th century, with the arrival of modern telescopes and large sky surveys, that astronomers began to realize the true scale of the cosmos. They discovered that our Milky Way is only one galaxy among hundreds of billions scattered across an expanding universe. But when scientists began mapping the distribution of those galaxies across enormous distances, they noticed something unexpected. The galaxies were not evenly spread through space. Instead, they formed an intricate cosmic web of filaments and clusters. And between those filaments were immense regions where galaxies were strangely absent. At first, astronomers thought these empty regions might simply be errors in observation. But as more data accumulated, a new picture emerged. These regions were real. They were enormous, and they would eventually become known as cosmic voids. Only in the second half of the 20th century did the scientific community begin to fully recognize their importance, revealing that the universe is not uniformly filled with galaxies, but instead shaped by a delicate and vast network of matter surrounding enormous cosmic emptiness. In the 1970s and 1980s, studies of redshift, the method used to measure the distances to galaxies, began revealing the large-scale structure of the universe. Galaxies were not scattered randomly through space, as scientists once assumed. Instead, they appeared to form a vast cosmic network, a kind of cosmic web, with enormous empty regions stretching between them. These empty regions became known as cosmic voids. With the advent of digital technology and increasingly powerful telescopes in the late 20th and early 21st centuries, our understanding of these voids expanded dramatically. Large sky surveys such as the Sloan Digital Sky Survey and the 2DF Redshift Survey produced detailed three-dimensional maps of the universe, allowing astronomers to visualize the cosmic web and the immense voids that shape its structure. The discovery and exploration of cosmic voids, from the earliest hints noticed by astronomers to the sophisticated instruments and surveys used today, represents a fascinating chapter in humanity's effort to understand the large-scale architecture of the universe. Yet, despite all this progress, these vast regions of near emptiness continue to puzzle scientists. One of the most striking examples is known as the Great Void. Even as astronomers study it in greater detail, fundamental questions remain. How could such an enormous empty region form in a universe governed by gravity, a force that pulls matter together rather than pushing it apart? As astronomers looked deeper into the cosmos with better instruments and more precise measurements, they began noticing a clear pattern in the distribution of galaxies. On the largest cosmic scales, galaxies are not spread evenly throughout space. Instead, they gather into clusters and elongated filaments that connect across enormous distances. These structures together form what cosmologists call the cosmic web. The web consists of dense clusters of galaxies, long threads or filaments connecting those clusters, and vast regions between them where very few galaxies exist. These regions are the cosmic voids. Compared with the crowded clusters and luminous filaments of the cosmic web, voids appear as enormous dark cavities where the number of galaxies drops dramatically. Recognizing this large-scale structure was a major milestone in cosmology. Scientists realized that voids are not simply places where galaxies failed to form. Instead, they are fundamental components of the universe's architecture, shaping how matter flows and evolves across billions of light years. And now that we have traced the path that led to the discovery of these enormous empty regions, we can turn our attention to one of the most mysterious voids ever identified. A region so vast that it has become legendary among cosmologists. Welcome to the Boötes Void, named after the constellation in which it lies. Discovered in 1981 by astronomer Robert Kirshner and his team, the Boötes Void remains one of the largest known cosmic voids ever observed in the universe. How big is it? For comparison, the diameter of this void is about 330 million light-years. If you could travel at the speed of light, it would take roughly 330 million years just to cross it from one side to the other. That distance alone is difficult to imagine. It is far larger than anything within our own galaxy. In fact, the Boötes Void spans a region vastly greater than the scale of the Milky Way. But the Boötes Void is not only enormous, it is also astonishingly empty. In a region of space where astronomers would normally expect to find thousands of galaxies, only a few dozen are actually present. Instead of the dense cosmic landscape seen elsewhere in the universe, this region resembles something closer to a cosmic desert. A vast emptiness surrounded by the luminous structures of the cosmic web. The existence of such a colossal void initially puzzled astronomers because it seemed to challenge the cosmological principle. The idea that on sufficiently large scales, the universe should appear roughly uniform in every direction. If matter were evenly distributed, regions this empty should be extremely rare. Yet observations showed that enormous voids are an essential part of the universe's large-scale structure, and the mysteries of the Boötes Void do not end with its size or emptiness. Some of the galaxies that do exist within the void appear to be arranged in unusual tubular or filament-like structures, a pattern that scientists are still trying to understand. These strange formations hint that even the emptiest regions of the universe may still contain subtle traces of the cosmic web. As our journey through these cosmic deserts continues, we arrive at another remarkable region of emptiness, one that has earned the impressive name supervoid. One of the most famous examples is the Eridanus supervoid, named after the constellation in which it appears. This is not merely an empty patch of space, but one of the largest structures ever identified in the observable universe. To appreciate its scale, consider this. The Eridanus supervoid stretches across roughly 1 billion light-years. Even if you could travel at the speed of light, it would still take about 1 billion years to cross it from one edge to the other. Compared with such immense distances, even entire galaxy clusters appear small. This supervoid is not completely empty, but the number of galaxies within it is dramatically lower than in surrounding regions of space. The contrast between this sparse region and the galaxy-rich structures around it makes the supervoid stand out clearly in maps of the cosmic web. What makes the Eridana supervoid especially intriguing, however, is not just its size. It may also be connected to one of the strangest anomalies ever observed in cosmology. A mysterious feature known as the cosmic microwave background cold spot. The cosmic microwave background is the faint afterglow of the Big Bang, a nearly uniform radiation field that fills the entire universe. Yet within this otherwise uniform pattern, astronomers have detected an unusually cold region in the sky. Some researchers have proposed that the Eridana supervoid might help explain this anomaly. As photons from the cosmic microwave background pass through such an enormous region of low-density space, they may lose a small amount of energy through a phenomenon known as the Sachs-Wolf effect. This process could potentially create the colder patch observed in the cosmic microwave background. Continuing our journey through these immense cosmic deserts, we encounter yet another extraordinary region of emptiness known as the Canes Venatici supervoid. Located in the constellation Canes Venatici, sometimes called the Hunting Dogs, this vast region provides another dramatic example of just how large and sparse some areas of the universe can be. Like other supervoids, this region contains far fewer galaxies than cosmologists would normally expect. The scale is staggering. The Canes Venatici supervoid is estimated to be roughly 1.2 billion light-years across, even traveling at the speed of light. It would take more than 1 billion years to cross from one side to the other. Seen in maps of the cosmic web, the region resembles a gigantic hollow within the otherwise intricate network of galaxies and filaments. It is another example of a cosmic desert surrounded by the rich forests of galaxies that dominate the rest of the universe. Yet the existence of such enormous empty regions raises a fundamental question. How did these voids form in the first place? What processes in the early universe could have led to such immense volumes of space containing so little matter? Although the exact mechanism behind the formation of cosmic voids is still being studied, astronomers have proposed several compelling theories that attempt to explain how these vast regions of emptiness emerged from the structure of the early universe. The first possible explanation for the formation of cosmic voids involves the concept of cosmic inflation. Scientists believe that shortly after the Big Bang, the universe experienced a period of extremely rapid expansion known as inflation, during which space itself stretched dramatically. During this brief but powerful phase, tiny quantum fluctuations in the density of matter were magnified to cosmic scales. These fluctuations created regions that were slightly denser and regions that were slightly less dense than average. Over billions of years, gravity gradually amplified these small differences. Matter slowly flowed toward the denser regions, eventually forming galaxies, galaxy clusters, and the long filaments that make up the cosmic web. Meanwhile, the less dense regions lost matter over time and gradually became the enormous empty spaces we now call cosmic voids. A second theory involves the influence of dark energy, the mysterious component of the universe responsible for its accelerating expansion. Dark energy may play a role in enlarging these voids by pushing galaxies away from already underdense regions. As the universe expands faster and faster, galaxies drift toward denser structures, while the emptier regions expand even further, effectively inflating the voids over cosmic time. A third explanation focuses on the natural development of large-scale cosmic structure. As gravity pulls matter together to form galaxies and galaxy clusters, matter does not collapse evenly everywhere. Instead, it gathers into a complex network of filaments and clusters, leaving vast empty regions between them. In this picture, voids are not unusual accidents, but rather an inevitable outcome of how gravity organizes matter across the universe. An easy way to visualize this process is to imagine a loaf of bread rising in an oven. As the dough expands, bubbles form inside it. The solid bread forms around the pockets of air, leaving empty spaces throughout the loaf. In a similar way, The universe forms structures of galaxies and dark matter surrounding enormous pockets of relative emptiness. These are only some of the ideas scientists are exploring to explain how cosmic voids formed. As vast and mysterious as these regions appear, they are likely just one piece of a much larger cosmic puzzle that researchers are still working to understand. The exact processes responsible for the formation of voids remain uncertain, and uncovering them is an extremely challenging task. One of the main difficulties is the sheer scale and complexity of the universe itself. The cosmos contains hundreds of billions of galaxies, each with its own unique structure and history. Understanding how all these galaxies interact and how they collectively shape the large-scale structure of the universe is an enormous scientific challenge. Another major difficulty lies in the mysterious nature of dark matter and dark energy. These invisible components are believed to dominate the mass and energy of the universe and play a central role in shaping cosmic structures, including the formation of voids. Yet our understanding of both remains incomplete. Without fully knowing what dark matter and dark energy actually are, determining exactly how they influence the growth of cosmic voids remains a difficult problem. Despite these challenges, research in this field is advancing rapidly. Scientists are now using increasingly powerful tools to explore the large-scale structure of the universe. Advanced telescopes and massive sky surveys are mapping the distribution of galaxies across enormous volumes of space, revealing the intricate structure of the cosmic web. One of the most important of these projects is the Sloan Digital Sky Survey, which has created some of the most detailed maps of the universe ever produced. These maps allow researchers to study the distribution of galaxies and identify the enormous voids that exist between them. At the same time, powerful computer simulations allow scientists to recreate the evolution of the universe inside virtual models. By adjusting the properties of dark matter, dark energy, and cosmic expansion, researchers can test different theories about how cosmic voids form and evolve over billions of years. With each new observation and each new simulation, scientists gain more clues about the origins of these enormous empty regions. Every new piece of data helps bring us a little closer to understanding how the cosmic web formed and why the universe looks the way it does today. Cosmic voids also have profound implications for cosmology and our broader understanding of the universe. These vast empty regions provide a unique environment for studying the influence of dark matter and dark energy, two of the most mysterious and dominant components of the cosmos. Dark matter, although invisible and undetectable by conventional telescopes, forms the gravitational scaffolding that shapes the large-scale structure of the universe. It is this hidden framework of dark matter that guides the formation of galaxies, clusters, and the enormous cosmic web that surrounds the great voids. Its gravitational influence helps shape the cosmic web of galaxies and voids that stretches across the observable universe. The very existence of these vast cosmic voids strongly suggests that dark matter played a crucial role in sculpting the large-scale structure of the universe we see today. Without the invisible gravitational scaffolding created by dark matter, galaxies would not have gathered into the intricate network of filaments and clusters that define the cosmic web. At the same time, dark energy, the mysterious force responsible for the accelerating expansion of the universe, may also contribute to the growth of these enormous voids. As space expands faster and faster, dark energy pushes galaxies away from regions that are already underdense. Over billions of years, this process can gradually enlarge the voids, causing them to expand on cosmic timescales and become even emptier compared to the surrounding regions of space. But the implications of cosmic voids extend far beyond simply mapping the large-scale structure of the universe. These immense empty regions provide valuable clues that can help refine our current cosmological models and deepen our understanding of how the universe evolved. In particular, the size, shape, and distribution of cosmic voids can serve as powerful tests of competing cosmological theories. If a particular model of the universe can successfully predict the number, scale, and arrangement of these voids. It strengthens confidence that the model accurately describes cosmic evolution. On the other hand, if observations reveal patterns that differ from theoretical predictions, it may signal that our current understanding of physics is incomplete and that new ideas or new theories are needed. In this sense, these great cosmic voids, once thought to be little more than empty gaps in space, have become important tools in humanity's effort to understand the deeper laws that govern the cosmos. Yet some researchers have wondered whether these vast regions of emptiness might hold even more surprising possibilities. What if cosmic voids are not simply empty space, but something stranger? This question has led to speculative ideas that extend beyond our familiar universe and into the realm of theoretical cosmology. One such idea involves the concept of the multiverse. The possibility that our universe may be only one of many universes existing alongside each other. According to some interpretations of modern theoretical physics, particularly certain models in quantum mechanics and string theory, additional dimensions beyond the 3 dimensions of space and 1 dimension of time may exist. These extra dimensions could potentially host other universes, each with its own physical laws, constants, and structures. Within this speculative framework, some theorists have suggested that enormous cosmic voids might represent regions where the structure of our universe becomes unusually thin or distorted. In such regions, the boundaries between dimensions might behave differently than elsewhere in the cosmos. In extreme interpretations of this idea, these vast voids have even been imagined as potential interfaces between universes. Places where our familiar 4-dimensional spacetime might interact with other dimensions beyond our perception. However, it is important to emphasize that these ideas remain highly speculative. At present, there is no direct observational evidence that cosmic voids connect to other universes or dimensions. They remain, first and foremost, natural structures produced by the evolution of matter and gravity within our own universe. Even so, the fact that such questions can be asked at all reveals just how mysterious these enormous regions of space remain, and how much we still have to learn about the deeper structure of reality. Although this idea offers an intriguing perspective and has inspired countless science fiction stories, it is far from being accepted by the mainstream scientific community. To this day, we have no concrete evidence for the existence of alternate universes or hidden dimensions beyond the ones we already know. Moving on, we encounter another fascinating concept, one that connects the immense scale of the universe with the incredibly small world of quantum physics. This concept is known as quantum fluctuations. In the quantum realm, particles and energy constantly appear and disappear in tiny bursts of activity, creating what physicists often describe as a restless, frothy sea of fluctuations. At first glance, these microscopic events may seem completely unrelated to the enormous structures we see in the cosmos. But the connection may lie in the earliest moments of the universe itself. Shortly after the Big Bang, the universe was extremely small, incredibly hot, and unimaginably dense. Under such extreme conditions, quantum effects may have influenced the structure of the entire cosmos. Tiny quantum fluctuations occurring during this early phase could have been stretched across vast distances as the universe rapidly expanded. As space expanded, these tiny variations in density may have been amplified. Over billions of years, gravity would then enhance these differences further. Regions with slightly more matter would slowly gather galaxies and clusters, while regions with slightly less matter would gradually become emptier and emptier. In this scenario, the enormous cosmic voids we observe today may actually be ancient imprints left behind by quantum fluctuations from the earliest moments of the universe. The great voids would therefore represent fossilized patterns in the fabric of space. preserved from a time when the universe itself was only fractions of a second old. It is important to note, however, that although this theory is compelling and supported by parts of modern cosmology, it still remains a hypothesis. Confirming such an idea requires extremely precise measurements of the large-scale structure of the universe, as well as a deeper understanding of both quantum physics and cosmic evolution. Nevertheless, the possibility that the smallest processes in nature could shape the largest structures in existence is one of the most fascinating ideas in modern science. It hints at a profound connection between the quantum world and the vast architecture of the cosmos. Another intriguing hypothesis takes us into the abstract mathematical field known as topology. The study of the properties of space and how those properties can change without breaking or tearing. In cosmology, topological anomalies or defects refer to irregularities that may exist within the fabric of spacetime itself. Just as a piece of fabric can contain imperfections or wrinkles, spacetime might also contain subtle defects formed during the earliest moments of the universe. These irregularities could represent regions where the normal structure of spacetime was slightly disturbed. To understand how such defects might have formed, we must again return to the period known as cosmic inflation, a fraction of a second after the Big Bang. During this phase, the universe expanded at an extraordinary rate, growing exponentially in a very short amount of time. Although inflation smoothed out many variations in matter and energy, it may also have amplified tiny irregularities within spacetime. These amplified irregularities could have produced topological defects embedded within the structure of the universe itself. Over billions of years, such defects might influence how matter moved through space. In some regions, matter may have found it more difficult to accumulate, gradually leaving behind vast regions of emptiness that would eventually evolve into the cosmic voids we observe today. Any discussion of cosmic voids would also be incomplete without mentioning another mysterious possibility connected to the early universe: primordial black holes. Unlike the black holes we commonly observe today, which form from the collapse of massive stars, primordial black holes are hypothetical objects that may have formed shortly after the Big Bang. These black holes could have originated from extremely dense regions created by fluctuations in the early universe. If such fluctuations were large enough, gravity might have caused those regions to collapse directly into black holes long before the first stars or galaxies ever existed. Now you may wonder what these ancient black holes might have to do with the enormous cosmic voids we have been discussing. One intriguing idea suggests that some of these vast regions of emptiness could actually contain large numbers of primordial black holes. These hypothetical black holes may have formed in the earliest moments after the Big Bang, long before the first stars or galaxies appeared. According to this proposal, cosmic voids might not be completely empty after all. Instead, they could contain populations of primordial black holes scattered throughout their immense volumes. Because these objects emit very little radiation, they would be extremely difficult to detect directly. Yet their presence would still influence their surroundings through gravity. Over vast stretches of time, their gravitational effects might alter the motion of matter in these regions, contributing to the enormous underdense structures we observe today. Another theory connects the formation of cosmic voids to the mysterious substance known as dark matter. Dark matter cannot be observed directly with telescopes. Yet, it is believed to make up roughly 85% of the matter in the universe. Although invisible, dark matter plays a fundamental role in shaping the large-scale structure of the cosmos. In cosmological models, dark matter forms a vast network of invisible filaments stretching across the universe. These filaments act like a gravitational framework, guiding the formation of galaxies and galaxy clusters. Ordinary matter tends to fall into these dark matter structures, gathering along the filaments and forming the luminous galaxies we observe. But what would happen if parts of this invisible network were disrupted? Some researchers have suggested that if certain dark matter filaments collapsed or dispersed, the flow of matter into those regions could be interrupted. Over time, This could leave behind enormous underdense regions, eventually evolving into the cosmic voids we observe today. In this sense, cosmic voids are not simply empty wastelands. They are dynamic regions that carry valuable clues about the structure and evolution of the universe. Studying them allows scientists to investigate how dark matter shapes cosmic architecture and how dark energy influences the expansion of space itself. The mystery of these great voids forces us to rethink many aspects of cosmology, from the formation of the cosmic web to the behavior of dark matter and dark energy. These vast regions of emptiness are helping scientists test and refine our understanding of the universe. And although we do not yet have all the answers, each observation and each new question brings us a little closer to uncovering the deeper structure of the cosmos. Every void we map and every galaxy we observe helps reveal another piece of the immense puzzle that is the universe. The next time you look up at the night sky, remember that the universe is not filled only with stars and galaxies. Hidden between them are enormous regions of near emptiness, cosmic voids stretching across hundreds of millions of light years. These silent expanses may appear empty, but they quietly shape the architecture of the universe itself. In their vast darkness, they preserve clues about how the cosmos formed and how it continues to evolve. Around 13.8 billion years ago, our universe began with an event we call the Big Bang. In that moment, space, time, matter, and energy emerged from an extremely hot and dense state and began expanding into the cosmos we inhabit today. Yet, even after decades of research, this beginning raises as many questions as it answers. What existed before the Big Bang? If the concept of before even makes sense, in a universe where time itself began with that event, is our universe a unique creation? Or only one chapter in a much larger cosmic story? Could the cosmos undergo endless cycles of birth, expansion, collapse, and rebirth? Some of the greatest scientific minds in history have proposed theories attempting to answer these questions. Each theory expands our imagination, pushing the boundaries of what we think we know about reality. And yet, with every answer we uncover, the universe seems to present even deeper mysteries, waiting beyond the horizon of our understanding. Some theories speak of other universes, while others imagine a cosmos that breathes, expanding and collapsing in an endless cycle. To understand these ideas, we must try to imagine what might have existed before the beginning of time itself. Picture a universe that behaves like a living rhythm. It expands outward from an initial state, growing larger for billions of years, and then slowly begins to contract, drawing all matter and energy back inward. This concept lies at the heart of the oscillating universe theory. According to this model, our universe may be just one phase in an eternal sequence of cosmic cycles. The universe expands, evolves, and eventually contracts again, only to be reborn in another expansion. In this picture, the cosmos has neither a true beginning nor a final end, only an endless sequence of transformations. Each cycle would begin with a Big Bang, an explosive moment in which space and time expand rapidly from an extremely dense state over billions of years. Galaxies form, stars ignite, and cosmic structures slowly emerge throughout the expanding universe. Eventually, according to this theory, the expansion of the universe would slow down under the influence of gravity. At some point, the expansion would stop entirely, and the universe would begin to contract. Galaxies would gradually move closer together as space itself shrank. Over immense stretches of time, this contraction would accelerate, leading to a dramatic event sometimes called the Big Crunch. During this final collapse, galaxies would collide, stars would be compressed, and all matter and energy would eventually be squeezed into an extremely dense state, resembling the singularity associated with the original Big Bang. But in the oscillating universe model, this collapse would not represent the final end. Instead, it would become the starting point for a new cosmic cycle. The compressed universe would expand again in another Big Bang, beginning the next phase of cosmic history. In this framework, each universe might last billions or even trillions of years, and each Big Bang would simply prepare the conditions for the next. The cosmos would behave like a vast cosmic pendulum, swinging endlessly between expansion and contraction, destruction and renewal. It is an elegant and fascinating idea. Yet the oscillating universe theory also faces serious challenges. Modern observations have revealed that the expansion of the universe is not slowing down. Instead, it appears to be accelerating, driven by the mysterious force known as dark energy. Measurements of the cosmic microwave background, the faint radiation left over from the Big Bang, also suggest that the geometry and energy content of the universe may not allow a future collapse. If the expansion continues accelerating, the universe may expand forever rather than eventually reversing into a contraction. Still, science is always evolving. Ideas once dismissed sometimes return in new forms when new evidence appears or when theories are revised. The oscillating universe remains an intriguing possibility that continues to inspire cosmological research. For much of history, humanity has thought of the universe as a single, unique bubble of reality surrounded by emptiness. But some physicists have proposed a much more radical idea. What if our universe is only one among countless others? This possibility is known as the multiverse theory. Imagine a vast cosmic ocean in which countless bubbles appear and disappear over time. Each bubble represents a universe with its own physical laws, its own history, and perhaps its own forms of matter and life. Within this picture, our universe would simply be one bubble among an immense cosmic foam. Some universes might contain different physical constants or additional dimensions beyond those we experience. Others might resemble our own universe closely, perhaps even allowing the formation of stars, galaxies, and life. Some theories even suggest that our universe might have formed through an interaction with another universe, triggering the Big Bang that began our own cosmic expansion. The multiverse concept dramatically expands our perspective on reality. It suggests that what we call the universe may be only a small part of a much larger and far more complex cosmic landscape. However, the multiverse idea remains highly speculative. One of the central challenges is that if these other universes exist beyond the boundaries of our observable cosmos, detecting them may be extraordinarily difficult. This raises an important question. If a theory cannot be directly tested or observed, can it truly be considered a scientific theory? Physicists continue to debate this question, and research into the multiverse remains an active and controversial area of theoretical physics. Even so, the idea occupies a fascinating place at the edge of human knowledge, where science begins to blend with philosophy and where observation gives way to profound questions about the nature of reality itself. And yet, even while contemplating the possibility of countless universes, it is worth returning to the one universe we know for certain exists: our own. Our understanding of the universe rests on two great pillars of modern physics. The first is quantum mechanics, which describes reality on the atomic and subatomic scale. The second is general relativity, which explains the behavior of gravity and the structure of the universe on the largest possible scales. But what happens when these two descriptions of reality meet? What happens when the world of the very small collides with the world of the very large? According to Einstein's theory of general relativity, space and time are not separate entities. Instead, they are woven together into a four-dimensional structure known as space-time. Massive objects such as stars, galaxies, and black holes bend this fabric of space-time. What we perceive as gravity is simply the result of this curvature. Quantum mechanics, however, paints a very different picture of reality. In the quantum world, particles do not behave like tiny solid objects. Instead, they exist as probabilities. A particle can occupy multiple states at once, appear and disappear in quantum fluctuations, and behave in ways that challenge our everyday intuition about how the world should work. These two powerful theories meet under the most extreme conditions in the universe. They collide in the singularity of the Big Bang and in the deep interiors of black holes, where enormous gravitational forces compress matter into incredibly small regions of space. In these environments, the effects of gravity and quantum mechanics become inseparable. For decades, physicists have searched for a theory of quantum gravity, a framework capable of reconciling these two very different descriptions of nature. One particularly intriguing idea that emerged from this search is the no-boundary proposal. Developed by physicists Stephen Hawking and James Hartle. According to this proposal, the universe may not have begun with a sharp singularity at all. Instead, space and time could be finite, yet without boundaries. Similar to the surface of the Earth, the surface of our planet is limited in size, but it has no edge. You can travel across it indefinitely without ever reaching a boundary where the surface suddenly stops. In the same way, the universe might behave like a four-dimensional analog of a sphere. In this model, the Big Bang would not be a point of infinite density, but rather a smooth beginning in space-time. Similar to the way the North Pole represents a special point on the surface of the Earth. From this perspective, asking what happened before the Big Bang becomes a meaningless question. It would be like asking what lies north of the North Pole. The question itself loses its meaning because the coordinate system ends there. This elegant idea provides one possible way to avoid the singularity problem at the origin of the universe. Yet, like many proposals in theoretical cosmology, the no-boundary model is still debated and continues to be studied by physicists. Even so, it represents a remarkable attempt to unite the largest structures in the universe with the smallest processes described by quantum physics. It pushes the boundaries of our understanding and forces us to reconsider how the universe may have begun. Another ambitious attempt to unify the laws of physics comes from the field known as string theory. In this framework, the fundamental building blocks of reality are not point-like particles. Instead, they are tiny one-dimensional objects known as strings. Each of these strings can vibrate in different ways, and each pattern of vibration corresponds to a different type of particle. Electrons, quarks, photons, and many other particles could simply be different vibrational states of the same fundamental strings. Much like different musical notes produced by the vibration of a string on a violin. But string theory goes even further. It suggests that the universe may contain more spatial dimensions than the three we experience in everyday life. In addition to length, width, and height, there may be additional hidden dimensions woven into the fabric of reality itself. These extra dimensions could be incredibly small, curled up in ways that make them impossible to observe directly with current technology. Yet, according to string theory, they may play a crucial role in shaping the fundamental laws of physics and the structure of the universe. These additional dimensions may be compactified or hidden from our perception, yet they could still influence the fundamental structure of reality. Within this framework, one variation of string theory known as the pre-Big Bang scenario, or more specifically, the ekpyrotic model, proposes a striking possibility. According to this idea, our universe may have been created by the collision of two enormous multidimensional structures known as branes, short for membranes, existing within a higher dimensional space. In this scenario, These brains drift through the higher dimensional cosmos until gravity gradually pulls them toward one another. When they eventually collide, the enormous energy released in that event could trigger something resembling a Big Bang, creating the hot, expanding universe we observe today. But the story does not necessarily end there. After the collision, the brains could separate again, drifting apart through the higher dimensional space. Over immense stretches of time, gravity might pull them back together once more, leading to another collision and potentially giving birth to another universe. If this model is correct, then what existed before the Big Bang might not have been absolute nothingness. Instead, there may have been another universe evolving on a neighboring brain, existing parallel to our own within a higher dimensional cosmos. Despite its elegance, however, string theory remains largely theoretical. While it offers a powerful mathematical framework capable of uniting quantum mechanics and gravity, direct experimental evidence for the theory has not yet been found. Detecting or testing the existence of extra dimensions or brain collisions remains extremely difficult with current technology. But what if we consider an entirely different approach to the question of the universe's origin? Instead of searching for a previous universe, we might reconsider the meaning of nothingness itself. When we imagine a vacuum, we often picture perfect emptiness. Yet in the world of quantum physics, the vacuum is anything but empty. It is a restless environment filled with fleeting activity. Tiny pairs of particles and antiparticles continuously appear and vanish within incredibly small fractions of time. This phenomenon is known as quantum vacuum fluctuations. According to one intriguing idea called the vacuum fluctuation model, our universe itself may have originated from one of these quantum events. In this model, a tiny bubble of what physicists call a false vacuum could spontaneously form within a quantum vacuum. Through processes such as quantum tunneling or phase transitions, this bubble might begin expanding extremely rapidly. As it expanded, the energy contained within this false vacuum could be converted into matter and radiation. Over time, this process would create the conditions necessary for the formation of particles, atoms, stars, galaxies, and eventually the complex structures we see throughout the universe today. From this perspective, the Big Bang might not have been the absolute beginning of existence. Instead, it could represent the moment when a tiny quantum fluctuation grew large enough to become an entire universe. In such a picture, what existed before the Big Bang may have been a quantum vacuum, an ocean of fluctuating energy where countless microscopic bubbles formed and disappeared. Our universe may simply be one rare bubble that expanded instead of collapsing. While the vacuum fluctuation model is fascinating, it also raises difficult questions. Why did this particular bubble grow into a universe while others faded away? And if the quantum vacuum exists eternally, how do we reconcile that with the finite age of our observable universe? As researchers continue exploring these questions, they are increasingly drawn toward new areas of study that attempt to merge quantum mechanics and cosmology, searching for deeper principles that might explain how universes can emerge from the quantum fabric of reality itself. That brings us to another fascinating possibility known as the Big Bounce theory. Imagine a universe that expands for billions of years, gradually slows down, begins to contract, and then suddenly rebounds, expanding once again. This is the core idea behind the Big Bounce model. Instead of collapsing into a singularity where the laws of physics break down, the theory suggests that our universe may have emerged from the final stages of a previous contracting universe. In this picture, the universe never compresses into an infinitely dense point. Instead, quantum effects prevent the collapse from reaching a true singularity. When the universe becomes extremely small and dense, those quantum effects trigger a transition. causing the universe to expand again in what we perceive as the Big Bang. Like the oscillating universe theory, the Big Bounce proposes a cosmos without a true beginning or final end. The universe could exist in an endless sequence of expansions and contractions, each cycle giving birth to the next. However, unlike the older oscillating universe model, the Big Bounce focuses specifically on the moment of transition, the instant when contraction reverses into expansion. So how does quantum physics enter this picture? At extremely small scales, quantum effects become dominant. One phenomenon predicted by quantum mechanics is known as quantum tunneling, where particles can pass through barriers even when classical physics says they should not have enough energy to do so. Some cosmological models suggest that the universe itself could undergo a similar quantum transition. As the universe contracts to an extremely dense state, quantum effects might allow it to tunnel through the collapse, bouncing into a new phase of expansion rather than forming a singularity. Despite its elegance, the Big Bounce theory remains highly speculative. Many questions remain unanswered. For instance, could we ever find observational evidence that our universe once passed through a previous phase of contraction? Could a complete theory of quantum gravity describe such extreme conditions accurately? These questions are still at the frontier of modern physics. Another major challenge lies in understanding the precise mechanism that would cause a collapsing universe to rebound without violating the known laws of physics. The mathematics describing such transitions is still incomplete, and current models struggle to fully integrate the concept with our standard understanding of time and causality. Yet, as often happens in science, competing ideas continue to emerge. Some physicists have suggested a radically different possibility involving an object we have already discovered but still only partially understand. An object both destructive and strangely creative. A black hole. Black holes are among the most mysterious objects in the universe. They form when massive stars collapse under their own gravity, compressing matter into an extraordinarily dense region of spacetime. Within a black hole, gravity becomes so strong that nothing can escape, not even light itself. At the very center of a black hole, according to general relativity, lies a singularity, a point where density becomes infinite and the curvature of spacetime reaches extreme values. It is a place where our current understanding of physics begins to break down. But what if such singularities are not simply endings? What if they are also beginnings? Some physicists have proposed that the singularity inside a black hole might give rise to a new expanding universe. In this idea, a black hole could act as a kind of cosmic seed, creating an entirely new region of spacetime within its interior. From this perspective, our own universe might actually be the interior of a black hole that formed in a much larger parent universe. In such a model, the Big Bang would correspond to the moment when that black hole first formed, with the expanding universe we observe representing the internal spacetime of that cosmic object. And the expansion of our universe may simply correspond to the internal growth of that black hole. If that idea were true, then the Big Bang would not have been the absolute beginning of everything. Instead, it might have been the moment a black hole formed in another universe, with our entire cosmos unfolding inside it ever since. In that strange and beautiful picture, every black hole scattered across the galaxies might contain a universe of its own, hidden beyond its event horizon, quietly expanding in a reality forever separated from ours. Of course, like many of the ideas we have explored tonight, this remains only a hypothesis. We do not yet know how such a theory could be tested. Could we ever detect traces of a parent universe beyond our own? Could the physics of black holes truly allow new universes to grow inside them? These are questions that continue to challenge the limits of modern cosmology. Another attempt to answer these questions comes from a theory known as loop quantum gravity, often abbreviated as LQG. This framework tries to reconcile the two great pillars of modern physics: quantum mechanics, which governs the smallest scales of nature, and general relativity, which describes gravity and the structure of the cosmos on the largest scales. According to loop quantum gravity, space itself may not be perfectly continuous. Instead, it could be made of incredibly tiny, discrete units, woven together like threads in an unimaginably fine cosmic fabric. When this idea is applied to the universe as a whole, it leads to a version of cosmology known as loop quantum cosmology. In this model, the universe never truly collapses into a singularity. As the universe contracts and becomes extremely dense, quantum gravitational effects begin to dominate and prevent the collapse from reaching an infinite density. Instead of ending in a singularity, the universe shrinks to a minimum size. Then something remarkable happens. The contraction stops, and the universe begins to expand again. This transition is often described as a big bounce, a moment when a collapsing universe rebounds into a new phase of expansion. From this perspective, the Big Bang may not have been the beginning of everything. It may simply have been the moment when a previous contracting universe bounced into the expanding cosmos we see today. Loop quantum cosmology even introduces a poetic idea, sometimes called a quantum bridge. This bridge is not a physical structure, but a transitional phase connecting one cosmic epoch to another, a passage between a contracting universe and the expanding one that followed it. Instead of a singular beginning, the universe would experience a quantum transition, a moment where one cosmic phase gives way to the next. If this picture is correct, then the Big Bang was not the start of time, but simply a turning point in an ongoing cosmic story. Of course, like many of the ideas we have explored tonight, this theory is still under investigation. It offers elegant mathematics and fascinating possibilities, but it has not yet been confirmed by observation. And so we arrive once again at the edge of what we truly know. Each theory we have explored offers a different vision of what might have existed before the Big Bang: a collapsing universe rebounding into a new one, a quantum fluctuation emerging from a restless vacuum, a collision of higher dimensional brains, a universe born inside a black hole. Some of these ideas may eventually prove correct. Others may quietly fade away as new discoveries reshape our understanding. But that is the beauty of science. Every answer we uncover opens the door to deeper questions. Every theory pushes us a little further toward understanding the extraordinary universe we inhabit. And tonight, after exploring these possibilities together, we are left with the most honest answer science can offer. We simply do not know what came before the Big Bang, but the search for that answer continues. Across observatories, laboratories, and quiet offices around the world, scientists are still studying the universe, still refining their models, still searching for clues hidden in the faint light of distant galaxies and the whisper of ancient radiation left behind by the birth of the cosmos. And perhaps one day, a discovery will emerge that changes everything we think we know. But for now, the universe keeps its earliest secrets hidden in the deep silence of space. So, as the night sky stretches above you, filled with distant stars and ancient light, remember that every point of light is part of a story still unfolding, a story that began nearly 13.8 billion years ago, and whose first chapter may still lie beyond our understanding. For tonight, it is enough simply to wonder. Let the questions drift slowly through your mind like galaxies across the cosmic web. Let the vastness of the universe settle into quiet perspective. And as the cosmos continues its silent expansion beyond the reach of our imagination, allow yourself to rest beneath the same sky that has inspired curiosity for countless generations. The universe is vast, its mysteries are deep, and the story is far from finished. Sleep well under the stars. And perhaps, somewhere in the darkness between galaxies. The answer is already waiting.